As you just noticed, we will record this talk, so it will be available afterwards for those who missed this date today. So welcome everyone in the name of the European Federation of Corrosion and Working Party 4 Nuclear Corrosion. I welcome you to this 5th edition of this online seminar on nuclear corrosion. We started this thanks to COVID 5 years ago in 2020, and every year around the World Corrosion Awareness Day, we have an interesting presentation for you. Before we start, I would like to remind you that if you are interested in the Working Party 4's activities, please go to our website. You see the link also in the chat, and also on our so-called EFC hub, which you also find the address here and in the chat. You can join, and beside Working Party 4, of course, there's also some other information available about EFC. And then this year, the Eurocore will take place in Paris. So I would like to advertise this one. The link you see here on my slide. And just for your information, we have in total received more than 900 abstracts, and just nuclear corrosion related sessions or talks, we have 62 at the moment, might change plus minus a few talks, and 12 posters. So from Monday to Thursday, we have a full program of nuclear corrosion related talks. So please come this summer or fall. Early registration deadline is June 15. And now it's time to start with our webinar, really. And for this, I hand over to Jan Stolel. He is from University of Chemistry and Technology, Prague, and he actually organized this talk today on nuclear waste corrosion issues. So Jan, please take over.
Good afternoon, everyone. Please let me briefly introduce Christofer Leygraf, the main speaker today, who is Emeritus Professor in KTH Stockholm in Sweden. And he is very well-known person in the corrosion community. On the Web of Science, he has got almost 300 articles, more than 11,000 citations, and Hersch Index 60. He is especially known for his achievements in atmospheric corrosion, but his activities, research activities, covers much wider range of topics, from the tiny biomedical implants to the huge canisters for deep geological repository. I'm very glad he agreed on giving this speech today, because he's bringing quite new approach, because usually we are solving interaction between the environment and the metal, the dissolution, changes in the solution, precipitation of corrosion products. But his approach is focused on the microstructural changes in the metal itself as a consequence of the interaction with the environment. So that's why I think it's extremely interesting and very important. So please, if you will have during his speech any question, please write it down to the chat. You can find it down on your screen as a Q&A icon. Yeah, write it down all, and then after I will try to sort the questions and exclude multiple questions for Christofer, and he will try to answer as much questions as possible. So enjoy the webinar, and Christofer, thanks much again, and the floor is yours.
Okay. Double click. Okay. Click. Okay. Well, first of all, Jan, thank you very much for your kind introduction. And good morning, or good afternoon, or good evening, everybody.
Christofer?
Yes.
We see another presentation. We don't see your presentation mode. You see 2 slides.
2 slides.
Yeah.
Okay.
Yes,
the next slide as well.
Okay.
Yeah.
Is this right?
Now it's perfect. Thank you very much.
Okay, look here. Okay. So now you see things. Okay, thank you. Well, the topic of this webinar is really something which is in harmony with our Corrosion Awareness Day, because it's something which is of profound societal influence, and it's something which certainly also relies on the corrosion resistance of materials. So this is really something that we are grateful that we can show here for a broader audience in this field. I want to acknowledge the co-authors of this presentation. They are from KTH Royal Institute of Technology, which have been doing the analysis, the preparation, and the transmission electron microscopy studies. Scientists also from Chalmers University of Technology, which have been performed the SIM studies. And then VTT in Finland, who have done the groundwater exposures. At the later part of this presentation, I will also present some colleagues from the University of Science and Technology in Beijing and from Delft Technical University, who have done computational studies, but we come to that later. The aims of this study is to explore the possible penetration and distribution of some elements from synthetic groundwater into copper, and to compare these penetrations at ambient temperature and at 60 degrees. This is really the technical challenge that we have tried to explore during the recent years. But first, since the organizers wanted me to give a short background about the situation in Sweden, here is something related to why Sweden was so early in establishing a method for the long-lived high-level nuclear waste. Sweden was actually, its first reactor was in 1954, a research reactor at our KTH university area. And between 1972 and 1985, 12 nuclear power reactors become operational at 4 nuclear power plants, all on the coast, the Swedish coast of south of Sweden. In the meantime, when this started, because of the increasing environmental concern, there was a debate also starting about safety issues, risk issues about the nuclear power reactors. And this resulted in a debate in the public media. And in 1976, there was an anti-nuclear, the Center Party, a political party, which led a political opposition coalition, requesting that nuclear industry had to prove a safe method and a safe site for disposal of long-lived high-level nuclear waste before license of any new startups of nuclear reactors could take place. By the way, all of this background is from a chapter by Dr. Johan Svan in Sweden, a chapter in a book, The Future of Radioactive Waste Governance, Lessons from Europe, which shows the situation in different countries about the storage of high-level nuclear waste. In the same year, 1976, the Swedish nuclear industry established a company, the Swedish Nuclear Fuel and Waste Management, SKB. And during the following years, SKB presented various versions for disposal of radioactive waste as a suitable site for the long-term disposal. In the mid-1990s, a finalization of the concept for long-term storing of nuclear waste called the KBS3 method was established. It consists of cylindrical copper canisters, 5 meters high and 5 centimeters thick, and they are encapsulating the spent nuclear fuel, also with help of cast iron canisters, in holes in the floor of tunnels at a depth of 500 meters underground in the granite bedrock. And then the tunnels and shafts are filled with a clay bentonite. And in 2009, a site south of the Forsmark nuclear power plant was chosen for the final repository. In Finland, which also followed the same concept for the KBS3 method, the site for chosen for the final repository is actually not far away from the Swedish one, just on the other side of the Baltic Sea, as seen here in Onkalo, Finland, while the Swedish side is Forsmark. In short, the KBS3 method for final disposal consists of 3 barriers, and you can see them here. We have the copper canister to the left here, which is, according to the theory, is thermodynamically immune. And for that reason, it was a main reason why it was chosen as a material for the KBS3 method. Outside of that, we have the bentonite clay, a buffer that swells in contact with water. And finally, we have the third barrier, which is the Swedish bedrock. And the copper canister of that then stored some 500 meters down in the Swedish bedrock. This is also of importance to mention the different responsibilities. We have on one hand the Swedish nuclear industry through SKB, which owns the responsibility for management and disposal of the nuclear waste. We have the Swedish Radiation Safety Authority, shortened SSM, which reviews the research and development of the method. The authority also prepares a government decision on nuclear facilities according to the Nuclear Activities Act. And then we have the Land and Environment Court, which reviews the whole process for long-term storage according to the Environmental Code, which is part of a judicial system to consider decisions that could have an environmental impact. And finally, we have the Swedish government that takes the final decision to allow and license the long-term facilities for their radioactive waste. After the licensing is finalized, SSM, the Swedish Radiation Safety Authority, in a stepwise procedure also approves the construction, trial operations, and closure in separate decisions. Over the years, we should say there have been quite a few scientific controversies regarding this method or parts of the method. From 1986 until now, there has been scientific evidence frequently presented and published that copper in contact with various aqueous environments, including deoxygenated water, may corrode faster than was originally assumed. There have been other reports also showing different opposite results. So there has really been quite a debate in this. But all of this came together in 2017 when many scientific controversies were debated during a 4-week process in the Land and Environmental Court. In this, SKB, SSM, and experts in corrosion, geology, and other areas took part. A recommendation from the Environmental Court said no to the corrosion-related uncertainties regarding the copper canister. For instance, the copper corrosion in deoxygenated water, the effect of hydrogen sulfide, and the effect of radiation. There was more information coming later on in the debate, and despite all of this, in 2022, the Swedish Social Democrat government took the decision to approve the repository. And the decision relied mainly on statements from SSM that in a holistic perspective, these 3 barriers together provide sufficient long-term safety. Yet, and this is one of our main arguments against this, is that the three barriers have never been tested together under fully operational conditions, that is, with radioactive waste in the copper canisters. And this now leads us to the current investigation. We see here a cross-section of the copper canister with a nuclear fuel inside. We can see, let's see if I can get the pointer. Okay. Yeah. Pointer. Oh, here it is. There, here. Okay, thank you. So we see that we have the nuclear fuel inside here. We have the copper canister here, the cross-section of it. We have the bentonite layer outside. And now we have different components like water from the outside, from the groundwater that in this scenario that might be in contact with the bentonite and then get through to the copper canister. We have hydrogen sulfide, we have chloride ions. All of these can be corrosive under certain conditions. And then we have from the inside gamma radiation. And the fundamental question to be explored in this study is, if groundwater passes through the bentonite and reaches the copper canister, will the elements hydrogen, oxygen, sulfur, and chlorine and other elements penetrate into copper? Or, as SKB and associates claim, these elements will not penetrate into copper, but only form part of corrosion products on the outside of the copper surface. This is the principal question. And for this reason, a collaboration started some years ago in which copper from the so-called SKB copper was wet ground to 600 degrees and then pre-oxidized in air for 7 days to simulate the oxide conditions before exposure. The chemistry of these groundwater, the anoxic groundwater, can be seen here. And there are a few components here which are more important perhaps than the other ones. One is the addition of 0.001 molar sodium sulfide. This is because of microbial activities which can form sulfides in the groundwater. And we have also sodium chloride. The exposure time has been 4 months. And then the ambient temperature is either 22 degrees or elevated to 60 degrees, two different exposure temperatures. And this is, of course, in complete accordance with the estimated temperature increase of the canisters to 80, 90 degrees during the first 100 to 200 years of repository. The first technique that we have been using, trying to analyze these different elements in copper after exposure to groundwater, is time-of-flight SIMS, time-of-flight secondary ion mass spectroscopy measurements. The experimental setup is seen here. I'm not showing the details, but basically it's an ion gun which hits the target, the sample here, is reflected through an ion optical system, and out comes the total area spectrum, out of which the distribution, the lateral distribution of different elements like sulfur or copper can be mapped with a lateral resolution of about 0.5 micrometer and an in-depth resolution of 1 nanometer. So this is quite a good tool for analyzing these elements, not only at the surface, but also inside the material. The next slide here shows the first results. This is from results and conclusions for oxygen. You see here, this one is the ambient temperature result. It's a square here, 450 by 450 micrometer. And you see the result as a function of depth down to about 100 nanometers. And you can see that there are in certain areas here, very narrow areas, oxygen can even be seen deeper inside the material. At 60 degrees, the same exposure, you see that the ingress of these elements is bigger. You can see it better here when we look at the results for oxygen. This is the result for oxygen as a function of sputtering time. You see that at ambient temperature, there is quite a narrow surface region only with oxygen, while at 60 degrees, you have a much larger ingress of oxygen into the copper material. This is the different grains that you can see, and they also show that the oxygen content in different grains differ. And these are just the grain boundaries. So there is a local penetration which proceeds along certain fast pathways. And there is definitely a deeper penetration of oxygen into copper at 60 degrees than at ambient temperature. And there is a variation of oxygen content between different grains. This is the same type of results, but now for sulfur. Again, if we go to this immediately, the result at ambient temperature is here. The result at 60 degrees is here. The ingress, the penetration of sulfur is even more pronounced than for sulfur than for oxygen. And again, there is a deeper penetration of sulfur into copper at 60 degrees than at ambient. And also, like for oxygen, a variation of sulfur content between different grains. So the results really show that oxygen and sulfur go deeper into the material. Here's a third element, chlorine. And here again shows the same type of results. The content is, or the ingress is not as pronounced as for the other two at 60 degrees, but definitely more than for at 60 degrees than at room temperature, and a variation between different grains. So the question is now, are these grain the grain boundaries, which are these fast pathways, or is it something else? So for this, we now go to the next two type of techniques that we have been using. And for doing this, we need to make quite an advanced surface preparation first. If we start with the sample, which was used for time of flight sims, we saw it from up here. Here's the grain boundary. And now we want to look at the grain boundary region deeper into the material. So what we do is that we put a line of platinum for surface protection. It's seen here. So we put, this is platinum, which is deposited on the sample. And then by peripheral focused ion beam milling, as seen here, we can now mill along the grain boundary, because the grain boundary is now deeper inside here, and the milling does not take the platinum. Platinum protects the fib milling. And when we go deeper inside here, we have been continuing this, then we are down, we start to see a microsample, which now contains the grain boundaries. So here's the microsample here. We can see the grain boundaries here. And this is now picked up. It's just very thin, about 20 to 40 micrometer long and about 10 to 15 micrometer broad. And we attach this microsample to a copper grid, and we thin it further down to about 200 nanometers for nanosims analysis, and further down for subsequent transmission electron microscopy analysis. So again, this is now a microsample which is perpendicular to the area that we saw from the beginning when we looked at this surface from the upside. So why are we using these techniques now? Nanosims is another secondary ion mass spectroscopy technique, again with a different, with an ion beam hitting the surface, and then we look at the analyzed scattered beams, but with a different ion optical system. The difference between the focused ion beam and the nanosims is that the spatial resolution here is about 10 times better than for time-of-flight sims. And also the hydrogen is much easier detected with this technique. And so there is a very high mass resolution, and there is a sub-parts per million sensitivity of hydrogen seen here. So the results that come out from this is that we have, we look now perpendicular to the surface before. This is now the, let's say, the reaction products from the outside for the copper surface. And then we have grains that we can see, and then we can look at the different elements inside the material also, if there are any. So here are now the first nanosims measurements to be seen here. We have the results up here for the 4 elements we have discussed: oxygen, hydrogen, sulfur, and chlorine. Here are the corrosion products at ambient temperature. And the corresponding results at 60 degrees are here. Here we can see that we have 2 different grains. And we can see that there is, in particular, for this result that we show first, we see that there is definitely an increased penetration of hydrogen at 60 degrees compared to the ambient temperature. We don't see at this a very pronounced difference between the between ambient and 60 degrees, but if we continue, we will see that. But we see another very important thing. We see several holes, like the one here, which is observations of holes at 60 degrees or pits at grain boundaries, which are characterized by an increased concentration of these elements. So it's something that goes on here with a much higher, we can say, activity, which is the result of the 60 degrees exposure. Here we can see more about the distribution of oxygen and sulfur. These are the results for ambient temperature. This is the results for 60 degrees. At ambient temperature, the corrosion products are up here. This is the one grain, this is the other grain, the grain boundary in between. And for ambient, you can see that we have done line scans here at different distances from the surface, from the corrosion products. And at ambient temperature, there is basically just background levels. There is nothing pronounced in the grains, and there is nothing pronounced at the grain boundary. But if you look at 60 degrees, we have a pronounced grain boundary enrichment of all these 3 line scans. We can see this for oxygen, and we can see this for sulfur. We can also see that inside the grains inside the matrix, that the levels of oxygen and sulfur are definitely higher than they are at ambient temperature. So all of these is now increasing evidence that the elements hydrogen, oxygen, sulfur go into the material at a much higher rate than they do at ambient temperature. But we want to have more information, and for this reason we have taken the same sample as I showed before with the Fib focused ion beam sample, but now we look at the microstructure along the same grain boundaries as we looked before. And you can see here now, this is at ambient temperature again, grain A, grain B. Now the corrosion products are down here, but it's basically the same area we look at. And if we select a small area here, this is the X-ray microanalysis for oxygen and sulfur. We just see oxygen and sulfur at the corrosion products. And with TM, if we magnify this area further, we have the corrosion products here, and we see very straight grain boundaries here, indicating that the microstructure, the grain boundaries don't undergo any particular change in structure. They are really straight lines. But if you take the results at 6 degrees, and here we select an area where we know that the grain boundary is. This is an area which is some few micrometers inside, away from the corrosion products. And we magnify it. Here is now the elemental distribution. And you can see clearly the green is oxygen, the red is sulfur, that oxygen has penetrated along the grain boundaries quite far inside the material, about 4 micrometers inside. It can go further, it is just a selected area. We can also see that there is a sulfur accumulation, these red areas inside the grains, not only at the grain boundaries. And if we look further with a much higher resolution, this is 10 nanometers now, we see that this is a whole grain boundary region, which looks like this. It's quite broad, and it is distorted. And as a result of the oxygen penetration into the grain boundaries, oxygen reacts with the surrounding copper and forms phases. You can see that here, nano-sized oxide particles. You can see from these lattice fringes that this is really a crystalline phase, and it's something that looks similar to a cuprous oxide. And because of that, the grain, there is an expansion of the grain boundary region, and the grain boundary becomes distorted like this. And you can imagine that if you have a distorted grain boundary region, the number of defects will increase considerably. And as it looks, sulfur is not seen as much here, but it's seen inside. So sulfur probably comes after oxygen because of the much higher defect regions. And then it clusters into areas, confined areas, where you see the sulfur inside the grains and far in the material. So the question is, how deep can this go? So what happens deeper inside the copper? And for this, we show the next technique, which is high-resolution synchrotron XRD measurements. This was done at DESI in synchrotron radiation facility in Hamburg. This is copper exposed 2 months at 60 degrees in synthetic anoxic groundwater. And I'm not showing all the details, but what the results show is that there is a significant lattice deformation extending several hundreds of micrometers into the bulk. And it's an in-depth gradient of lattice expansion to about 90 micrometer near the surface region, and a lattice contraction beneath this expansive region. And this can be explained again by the insertion of different elements into the microstructure. We had oxygen coming first to the grain boundaries. We have sulfur going into the deeper into the grains, and also hydrogen. And this, of course, results in a dilation and metal bond weakening. So all of these results really go together and show that there is a deep ingress of these elements at 60 degrees, which cannot be seen at room temperature, and it has implications far inside the material, much further inside than we ever had expected. But this also then goes to the next question: what happens after a long time? Actually, here are some SIMS analysis after 7 years of exposure in conditions similar to the final disposal. And these results show that this is the hydrogen results as a function of depth of the copper canister. And what they show is that actually hydrogen penetrates throughout the whole 5 centimeter copper canister thickness after 7 years. This is in the heated repository. These results, of course, at that time, they were published earlier, could not be understood really, but in view of the new results that we see here, where we really can see the detailed microstructural changes that occur and the introduction of these elements into the material, this now comes into another view, another perspective. So after 7 years, the results really show that all of hydrogen has penetrated through it. Sulfur and oxygen were not measured in these conditions. So the conclusions so far: copper exposed to synthetic groundwater for 4 months with addition of 0.001 molar sodium sulfide has been analyzed with time-of-flight SIMS, nano-SIMS, and TEM, and high resolution XRD, which goes to a deeper depth, to a few hundred micrometers, the last technique. There's really clear evidence of penetration of these elements at 60 degrees, which is strongly promoted by temperature. And we see that oxygen is observed along the grain boundary and forms phases, which distorts the grain boundary region. And this results in an accelerated transport of sulfur and hydrogen along the grain boundary region and transport into the grains, and accumulation of sulfur in confined areas of the matrix. The lattice deformation extends several hundreds of micrometers into the bulk at 60 degrees, leading to metal-metal bond weakening. And interestingly also, we see certain holes or pits crossing the grain boundaries inside the material, which are enriched in sulfur, oxygen, hydrogen, and chlorine. And the penetration that we see of hydrogen after 4 months supports, can we say, early observations up to 7 years. Of course, the rate by which hydrogen penetrates is not any simple fixed diffusion laws. These are very complicated rate laws. Of course, when we found these results, we were to begin with quite surprised. We didn't expect that there wasn't penetration so high at 60 degrees. But in fact, there have been other observations of accelerated corrosion of copper at relatively low temperatures. There is a phenomenon called ant nest corrosion, which is a frequent failure mechanisms in heat exchanger copper pipes. It also occurs after shorter times, months typically, and relatively low temperatures, typically below 100 degrees Celsius. Here's just one example of a result showing the cross-section of a copper wall. And you can see that this is ant nest corrosion of a heat exchanger copper pipe after 2 months of service. And there are several other examples when we look into the literature. So this is actually nothing particularly new, but the mechanism is a little bit different. The initiation of ant nest corrosion is from the outside. It's external, so it's like pitting corrosion. But the rapid progress that makes this go so deep into the material at a few months, and we see here we go typically maybe 100 micrometer into the material, is that the ant nest corrosion may also be facilitated by the rapid transport of oxygen, sulfur, hydrogen, and so on into the material at the elevated temperatures, like we have seen here. Okay, this is now what happens without radiation. And the next question is, what happens with radiation? And all of the results I've shown now have been without radiation, but I want to emphasize that radiation can have a profound influence on these results. These are, what I'm showing here, is results from a doctoral thesis that is about 10 years old, here from our university, Åsa Björkbacka, supervised by Professor Mats Jonsson, Professor Nuclear Chemistry. And what you see here is the amount of dissolved copper in deoxygenated water as a function of dose of gamma radiation. Here's from 1 kilogray up to 100 kilogray, which corresponds roughly to the absorption after 100 years in a deep repository. So of course the radiation rate is higher than it is in natural conditions. But what it shows that there is a very clear dose effects. At a given dose, also the effect increases with a reduced dose rate. So if you take any result here, let's say at a certain dose here, you will see that there is a tendency that the higher results, that means the higher amount of dissolved copper, the more corroded copper, is shown at a lower dose rate. The interesting thing here is that this is the radiation effects on corrosion is orders of magnitude higher than what can be explained by the pure temperature effect of radiation and what can be explained only by the presence of radiolysis products, hydrogen peroxide or the OH radical. And this shows that the whole KBS3 concept needs to be investigated at real exposure conditions. If we want to consider all these effects together, the effect of radiation in combination with the complex microstructural changes we saw from the exposure of synthetic groundwater, we cannot study each individual phenomena and its influence by gamma radiation. We have to put everything together, and this has never been done. So the final consideration here is that internal corrosion, that means corrosion processes in the interior of the material, may be even more important than the external ones. And I hope I have convinced you by the results shown. We also need to consider the influence of radiation and of temperature together with the exposures that we have seen. So the total SKB3 concept for long-term storage of nuclear waste needs to be tested as an integral part, including all three barriers and the spent fuel during exposure at real field conditions and radiation. And our conclusion from this is that in view of all new findings on internal corrosion with concomitant risks for hydrogen-induced embrittlement or sulfur-induced stress corrosion cracking, or unknown effects by radiation temperature, the fact that the KBS3 concept never has been investigated at real field exposure condition, we can question copper as a canister material for the long-term storage of nuclear waste until more evidence has been presented, much more evidence. Okay, this is the study as this had been done at our university, but we have in the last year started a collaboration with the University of Science and Technology in Beijing, headed by Professor Chow-Fang Dong, and Delft Technical University in Netherlands on computational studies, because we want to give a more fundamental background for all of this that happens, which is still quite unexpected to us. And here is the unique thing, I should say, about these computational studies, that they are based on the real microstructure from our TEM studies. So here are the grains with their orientations, a grain A, grain B, and there's a third grain here, as they have been determined by transmission electron microscopy and also by SIMS. And this has then been used as the input for the computational studies. These density functional theory calculations that have been used here are based on real atomic configurations from these different microstructures that we have seen. And they're therefore being combined with machine learning and molecular dynamics, because there are so many different configurations that have to be included in this in order to optimize and get a molecular dynamic potential that can be used. So we can say that all of these results so far are preliminary, but we want to explore by this the difference in penetration of elements between grains and grain boundary, the difference in penetration of elements between different grains, the difference in penetration between oxygen and sulfur, and the difference in penetration between 22 and 60 degrees. All of this, again, to get a better view on why we get such big difference between 22 and 60 degrees. So the final slide here shows example of some preliminary computational results. Here we see the penetration of oxygen. You can recognize here, this is grain B, this is grain A, these are the corrosion products. But we can also see this oxygen here, how it can go, if you go over to this one here, that the oxygen can go deeper into the material and along the grain boundaries. So there's really also seen here a penetration of oxygen along the grain boundaries. We can also see through something which is quite complicated, but look at the pair separation distance between different species between different elements in grain A and grain B, that in grain B here, you have something along a distance which is quite close to cuprous oxide, and which suggests that, as you can see also here, This is now deep into the material that, as a result of the enhanced penetration of oxygen, we form cuprous oxide in a region between grain A and grain B. So this is maybe a little bit quite advanced, and I should emphasize again preliminary, but the interesting thing is that it seems to show the same type of phenomena with internal corrosion as a result of cuprous oxide formation along the grain boundaries. So we are quite clear that there is something quite enhanced occurring deep inside the copper material at 60 degrees. So the overall conclusion is then that the combined experimental and computational approach will provide new insight into internal corrosion processes of copper and a ramification for considering copper as a canister material for the long-term storage of nuclear waste. Thank you for watching and for your attention. And I'm happy if I can answer some questions.
Okay, thank you very much, Christofer, for such a very nice talk. So I will try to read the questions for you. So the first question is from the anonymous attendee. If could a canister with graded wall thickness, it means pure copper in the internal diameter and gradually changing to brass in the outer diameter, could it solve this problem?
We have considered actually to also look at other, maybe I can take this away and I can show my,
out?
yeah, can go. Let's see if
I've stopped.
I stop sharing.
You want to say something else?
Yeah, I can. Yeah. Okay. I can. We have been thinking of if alternatives to copper could be used. The problem is that we have no data at all for any alternatives to pure copper. We think from other studies that there is a very interesting alloy. It's called the golden alloy, and it contains, besides copper, also aluminum and zinc and tin. And that is quite an interesting alloy because it has much more functions than just the basic copper. But again, there are no, we have no real background studies on this topic, so I really can't tell anything about it.
Okay, thank you. The next question is from the Clayton Bivas on the TÜV-SIMS depth profile area maps of the oxygen and sulfur intensity towards the start of the presentation. How did you map the position of the grain boundaries on the SIMS map?
We should maybe go back here. Yeah. Sharing again, yes. Okay. Okay. Yeah, we have to go back here. Let's go to one of these slides. The time of flight sims, yes. One more. Okay. Can I put this away? Oh. Okay. Well, the point is that the thing is that by this ion gun and the optics, you see you scan not only laterally along the surface, but you scan also with as a function of depth. And with this technique, you cannot really tell if these areas for enhanced penetration really like this one. You can see here that there is something which could suggest that this is a grain boundary. But in fact, you cannot tell this surely by the time of flight SIMS measurements. You have to combine this with the other techniques that we have been using, so that you are quite clear that the areas are really grain boundary regions and nothing else.
Great, thank you. And the next question is from Ben Hackett. How do you explain the penetration being fivefold as deep when the temperature is only increased by 40 degrees? Does the diffusion process follow an Arrhenius relationship?
We don't think it's an Arrhenius relationship. It must be something much more complicated. I mean, if there was an Arrhenius plot, and if there were just diffusion laws according to Fick's laws, then these relations would be much simpler. But the fact that we see that the transport, the penetration goes along the grain boundaries, but since the grain boundaries become much more defected, much more full of dislocation, for instance, when you go from room temperature to 60 degrees, this is much more complicated than just saying that this should be an Arrhenius behavior. So we really need to look carefully into the whole microstructure in order to understand why this enhanced penetration occurs. And this is one of the reasons why we have asked our colleagues in Beijing to do these quite advanced molecular dynamic studies so that we can also see, where they look at different atomic configurations, including defected configurations, to see and try to explain why this is so enhanced, this penetration. Yeah, we have, of course, also the Antnet corrosion, which also shows this type of behavior, as I also showed you, and something called one-dimensional worm form corrosion, which has recently been published in the literature. And both of these suggest that there is quite an enhanced penetration at elevated temperature. But again, it does not follow any simple Arrhenius plots at this point, as we can see it.
Okay, there is just one congratulation from Walter Bogarts. And Miran Behazin would like to ask if you could explain why the transport of sulfur and hydrogen are assumed to be accelerated when the grains are distorted.
Sorry, can you repeat the last sentence, Jan?
Yeah. If you could explain why the transport of sulfur and hydrogen are assumed to be accelerated when the grains are distorted.
This is because of the yes. Here we are. Again, if you compare the difference in results between room temperature or ambient temperature, you see these very straight grain boundaries at room temperature, and you see these very distorted grain boundaries at 60 degrees. And we see also by TEM that there is a much higher concentration of defects at 60 degrees. So all these defects facilitate the transport of sulfur and hydrogen deeper into the material. So it's really a result of the microstructural changes that occur during the exposure at 60 degrees, which does not occur at room temperature. So this is the explanation as far as we can say it right now.
Okay, other question from anonymous attendee. If the radiation effects are higher at lower dose rates, then the worst case must be when there is no radiation.
The worst case, we can go back to this one, yes. Yeah. Yes. Okay, so all of these results were at 3 different dose rates, 80 up to 770 grays per hour. And so the result at a certain dose, let's say this one here. Oh, yeah. Okay, yeah. So on an average, if we take any dose rate here, we see that there is a tendency that the corrosion or the dissolution of copper is lower at a certain dose rate and a given dose. So it's not a clear tendency, but there is a tendency. You see the blue ones here are the dose rates, the lowest dose rates. They are up here and up here and up here. They seem to be giving a higher corrosion at a given dose. But again, the trend is not absolutely clear, but there seems to be a trend like that too. So the important thing here is that even if you would go down to natural, the gamma radiation that you have in the real repository conditions, what these results tell us is that these results may still be quite relevant, because they show that when you go down to the lower dose rates, they still might be quite pronounced corrosion effects. But of course, again, when we go down to the real conditions, we have no results for that. We have never seen everything, the whole KBS3 concept tested with gamma radiation inside. So as long as we cannot do that, we cannot really tell, considering all these observations we have here, what will really happen under the real repository conditions.
Okay, and there is a next question from Anna Golubko. What temperature is then suitable for copper canisters if 60 degrees C is too high and there is a risk of corrosion? Considering the concepts of other countries, some operate with the temperature of 90-95 degrees C on the boundary between outer canister wall and surrounding buffer.
Well, again, the temperature that we have only been testing 2 temperatures, ambient and elevated temperature. And as you know, under the conditions that there is an estimated temperature increase of the copper canister to about 80 to 90 degrees during the first 100-200 years in the repository. So these are the temperature effects that we will reach given these conditions, this concept. So we cannot choose any temperature. We have only what we have seen here. As you go to 60 degrees, you see these dramatic effects. Of course, if we would go out up to 80 degrees or 90 degrees, the effects would, of course, be even more pronounced. That we can be quite sure of. We have just chosen this 60 degrees as sort of an average temperature for the 100 to 200 years in the repository.
Okay, next question from Walter Bogarts. Do you think we could see similar phenomena in austenitic or super-austenitic stainless steel?
This is, I think, a very important question. I think we know very little about the other materials. And this is also the principal, I would say, most important information to the community working with this issue is that you really need to explore the other, the inside of the materials as well. I mean, corrosion by tradition has been something that we think it always starts from the outside. And we have looked at outside observations of things that happen. But we realize, of course, that when it goes deeper into the material, something can happen there too. And what happens with an austenitic stainless steel? I don't know. But one thing that strikes me is that, you know, you have something called the critical pitting temperature, which is a very well-established measurement of the corrosion resistance of stainless steels, where you polarize your sample and you then analyze where pitting starts or where you get a certain current at a certain temperature. And these temperatures are quite low. I mean, they are in the range of 50, 60 degrees, which obviously show that things happen. There are things that happen even in other materials than copper at these temperatures. Of course, there is no immediate connection between critical pitting temperature and the studies we are doing here. But it just shows that we could expect things to happen at much lower temperatures than traditional high temperature oxidation or corrosion, which usually is measured at temperatures above 300 or 400 degrees or higher. So this is it's a very important question.
And there is another question from anonymous attendee. I would like to know more about the work that was done to characterize the starting material. You have given very specific example of how elements penetrate into copper at elevated temperature, but the SKB copper contains both oxygen and sulfur. So how can you be certain that you haven't found pre-existing clusters of oxygen and sulfur?
Oh, you mean that the oxygen and sulfur was there before the exposure was done? Well, we can see that if we just compare it with the room temperature exposures, we see very little oxygen and sulfur. So the room temperature results show that oxygen and sulfur are not there to any large extent at all. And even then, they come from the synthetic groundwater. So we can be quite sure that whatever we see in terms of an enrichment of oxygen and sulfur comes from the elevated temperature, going from room temperature to 60 degrees.
And there is a new question from anonymous attendee. For ICP-OES solution analysis of copper samples, would you expect to see different corrosion species forming at different dose rates? And would their solubilities differ, influencing the preserved corrosion rate based on the copper solution concentration?
Again, can you repeat the last sentence? I didn't get.
Yeah. If the ICP-OES solution analysis of copper samples, if you would expect to see different corrosion species formed in this at different dose rates, and if their different solubilities could influence the preserved corrosion rate.
Yes. I should go back to look at the doctoral thesis that was done. As far as I remember, there were some changes in the corrosion products form. But I also remember that cuprite was the main phase observed under these conditions in anoxic water with a radiation. But there might also be some other, not only cuprite, I mean, that's the copper 1 oxide, but also to some extent copper 2 oxide, the tenorite. But I don't think that there is such a dramatic change in the composition of these corrosion products at different dose rates. But there is this radiation, the doctoral thesis about this, which show it. Let's see if I can go back to Åsa Björkbacka. Yeah, let's see. Yes. This is the main author, Åsa Björkbacka, and these are one of the papers, but she published several. This is in radiation physics and chemistry. And I know that in some of these, also the corrosion products were measured. But I don't think that's a critical issue, the composition of the different oxides, but the interaction between the radiation, water, and the oxides was critical also. But I don't know the details of this.
Okay, we have one question which slipped into the answered Q&A from Jian Chen, who has a couple of questions. The first is, what's the dissolved oxygen concentration in the experiments?
Well, the oxygen concentration in the material, this is oxygen OFP copper. This is oxygen-free copper. So we don't expect it. We don't expect the oxygen-free copper. In the copper is in copper the content is oxygen-free. What the exact concentration is, of course, there's always copper present, but to a very, very low extent. And in the solution, in the exposure, it's also oxygen-free. So it's a very low amount. I don't know. Do you know if what the actual concentration is? No.
We got it as a 0.
Well, it's nothing is 0, but it's very low anyhow. Yeah. So we must assume that in both in the oxygen content in the copper and in the exposure is from the beginning is oxygen-free, but of course it contains water anyhow, where oxygen comes from.
Okay, maybe this question was about dissolved oxygen in the environment, because the second question is, how did you ensure the anoxic conditions as claimed?
It was through the electrochemical, we can say through the electrochemical measurements of in the potential. Yeah, the potential. So the potential tells us which the oxygen level in this, if it's anoxic or not. Yes.
Okay, and the third question is, in the pits, the detection of oxygen suggests the formation of oxides. In the presence of sulfide is thermodynamically more stable than oxides. Can you explain how the oxides formed? Does it mean that the experiments were leaking?
You mean the experiments of the where in the corrosion products, or where?
Yeah, in the pits. It was probably about that. You know, you have shown the pit with TOF analyzed. I guess it's touching this problem.
Yeah, generally speaking, the oxygen is not coming directly from the copper. It's not directly coming from the solution, from the groundwater, but it comes from the water, which dissociates in different ways. And from that, then the whole process starts. So obviously, after a few months of exposure, you really can see, as I showed here, at the elevated temperature, that oxygen really is formed and goes into the grain boundaries, as it does here. And then, of course, it might also be other effects that show this hole that could be seen in one of the slides, which also showed that oxygen and sulfur was present in the hole, which could be very similar to the type of holes we see in antnet corrosion. So there are many ways in which oxygen and sulfur can enter into at the elevated temperature at 60 degrees.
Yeah, we have other question from anonymous attendee. As an inspector in the corrosion and coating field, where would protective coatings fit into the evolution of corrosion studies on different materials? Will we perhaps one day move away from protective coatings and rather engineer the materials to a point where they cannot corrode? What do we wish to achieve with the studies into this type of materials?
You mean if you should go away from these type of materials and go where? You mean?
If I understood, probably to coatings, or the other way to maybe abandon coatings. I don't really understand these questions. Sorry.
I think it's a very general question. I can't really tell if our results here can provide any new information to that question. I can only say that as if even the copper as a bulk material has been penetrated by hydrogen after a certain exposure time, and even by the other elements. So a coating would of course be penetrated much quicker. But then the question is again, how do other materials behave in comparison to copper? And that question we cannot really say. We have only done these studies on copper and not on any other material. But again, we want to emphasize the phenomenon of internal corrosion, and that this is really something that might occur on many other materials as well.
Okay, I'm just checking also the chat, because from Q&A we have answered all the questions, and in the chat we have a couple more from Darius Boffa. Will heat treating the copper to make it harder not assist with unwanted elements penetrating the grains?
Yeah, who knows? I mean, we have, if you heat treat, you get another microstructure, and how that microstructure might react towards these results is something that is hard to tell from these results. So you really need to, you cannot predict anything. All of these results have been done for OFP copper, that means SKB copper, and nothing else. So if you start to do heat treatments, it depends on how you do them and how they change the microstructure. So.
Okay, the second question is if the cathodic protection would assist in the reduction of corrosion.
It's hard to tell from this.
Yeah, I see, because this is very frequent question for these temporary, prevention methods of corrosion, but it's not a long-lasting method. It's not sustainable for many years.
Yeah.
It's the same question for the coatings, which would be disrupted by the gamma ray, and it's really difficult to provide anything what's really temporary.
Exactly. So I don't think cathodic protection is not an issue.
Yeah, definitely. Yeah, and now maybe we're at the end. So if I may, I have just one quick question, because it's very interesting that if I understood it well, so at the beginning, the diffusion proceeds in zero-valent atoms of these elements, but then they can form some new phase, whatever, oxidic or sulfidic. So in that case, we could block a bit this grain boundary. So in fact, even if we have this very quick diffusion at the beginning, it could decelerate quite significantly in the time. Do I understand well?
If you mean if the oxides or the sulfides, if they block?
Yeah, the grain boundary.
Okay. Well, in the beginning, you have the of course the corrosion products that are formed, and they do form a certain blocking, you can say, in particular at room temperature. I think this is quite clear. But at 60 degrees, you see that there is no big protection of these sulfides and oxides. You see them by the different techniques we have used. We see that we have corrosion products of oxides and sulfides, but we also see that there are no protection. The elements still go inside the grains at these under these conditions, and these are really natural conditions where we have the copper exposed to groundwater and nothing else but 60 degrees. So the protection of oxide and sulfide is maybe there, but it's definitely not enough to allow the elements to penetrate into the copper, as can be seen on these results.
Okay, thank you. So one last check if we have some new question. Don't see any. So thank you very much once again, Christofer, for such a nice talk and really also the great discussion. And I would also like to thank the audience that they were employed in this very active discussion. Thank you very much for that.
Okay, thank you too. Thank you for arranging this. It was very nice to give a presentation of all our results. And we will be back in Paris in the nuclear materials session to give an extended talk, of course, a much shorter talk, but it will also contain, hopefully, some of the computational results into this. Hopefully, they will get closer to our experimental results. So thank you for arranging this.
Thank you also from my side, Christofer and Jan, and all the listeners. We had, I think, mostly were 63 attendees, which is a very nice number, I would say. And as Christofer said, come to EuroCorr, you will hear more from him and from many other presenters, some interesting presentations. So bye-bye, everyone.
Bye-bye.
Thank you. Bye-bye.
Bye-bye.